Hey there, this is Dr. B, and let's take a look at how substances can be affected by pressure and temperature. We got ourselves a cup of coffee here, and suppose we heat it up. Well, it's going to boil. But what if we pressurize it? Students aren't always completely familiar with how that works. But let's think about it. If you take a liquid substance like this cup of coffee, we can bring it to boil. It almost looks like it's already hot. I see a little steam up there. By increasing the temperature or lowering the pressure. As you decrease the pressure, the boiling point goes down. Perhaps if you live in the mountains, you see that in real terms, right? You see that when you're at a very high altitude that you've got to heat your food longer in order for it to cook. Reason the boiling temperature isn't as high. And to look at this from a fairly unusual perspective is to think about what's happening when we do that. And to do that, let's consider what's going on above this liquid. Above this liquid, there are some water molecules, and you're probably not surprised to hear that that would be true even at room temperature. It would be evaporating a little bit. So you've got a certain amount of the pressure due to the water molecules in this case. Heat it up and it becomes more. And we call that vapor pressure. As you heat it up, you get more vapors above it, and so the pressure that's due to those gases will be higher. And let's go a little bit further. Once you hit 100 degrees Celsius at atmospheric pressure, well, it's just all gas. So the pressure above here is the same as there because it's all gas. You've heated it up to the point where the vapor pressures are equal. When you lower the pressure, which is something we're pretty unfamiliar with in general, you need a bell jar or some special device to do that. You can accomplish the same thing by just making that the vapor pressure here equal to there. Now, I know that's a little weird, but that's vapor pressure for you. If you heat it up, you equalize the vapor pressure. If you decrease the pressure of the liquid, you also equalize the vapor pressure, which is defined as the pressure of a gas over its liquid or solid form. Let's take a look at two different ways we can really take a look at pressure and temperature interactions. And let's make sure we focus a little bit on the pressure part, since that's the part that people are a little less comfortable with. Here we have what they call a pressure-temperature nomograph, which is mostly dealing with just liquids and gases. Here we have a phase diagram that also includes solids, but the coordinates are the same, pressure versus temperature. Or if you will, what happens when you mess with pressure and temperature for liquid gas systems or liquid gas solid systems. We've got four pretty common substances. Diethyl ether, which boils in the palm of your hand. This is millimeters of mercury, where 760 is an atmosphere. So that's just normal sea level pressure there. You stick this thing in the palm of your hand and it will go from the liquid to the gaseous phase. But if you reduce the pressure down, that boiling point will also go down. So if you're climbing up a mountain, you might get to the point, if the mountain's big enough, where the boiling point goes below room temperature, and it boils simply by reducing the pressure. Ethanol will also, if you heat it up, can turn from a liquid to a gas, but it's not till you go down to insanely low pressures. That looks like 1/7 of an atmosphere or less, that you can get that stuff to boil at room temperature. Water, even lower, we'd have to go to, I would estimate, a pressure like that. Oh, very good, a very strong vacuum. Maybe 1/20 of an atmosphere, something like that. And if you take a substance like ethylene glycol, it looks like even if you bring it down to just about no pressure at all, which, by the way, is super hard to do, that thing will still have a boiling point of 60 degrees. It'll stay as a liquid. Perhaps it's not surprising that ethylene glycol is known as antifreeze. So that's a little bit pressure versus temperature. As a scientist, we used to use these things to say, like, oh, I want to distill this. What am I dealing with here? How kind of a vacuum do I need to generate in order to get a convenient boiling point? And this is the big picture here, a phase diagram. Not only liquids and gases, but solids as well. And it's almost more of an astronomical interest because a lot of substances, let's face it, virtually all the substances don't sublime or deposit. Carbon dioxide, naphthalene, some substances do, but not many. Most do the solid to liquid to gas conversion. But if you're dealing with crazy pressures, usually, like I'm talking like typically very low pressures, you can get this sublimation and the opposite form deposition to occur. So even water, perhaps, if you brought it down to a strange low pressure, could go to the solid form, directly to the gas form, without ever getting wet. Pretty interesting, really, but it's oftentimes extreme. And if all that's true, you must have something called a triple point where all three can possibly exist. I think I'll stop there because especially if you happen to be studying AP chemistry, they don't go too deeply into this, just to understand the basic format here. Okay, that's a look at how substances are affected by pressure and temperature.